try that again. And start this. Okay, and I would say we can go ahead anytime.
All right, well, welcome everyone. I'd like to introduce Jongjin Seo. Jongjin hails to us from South Korea, from the city of Daegu, where he attended Kyungkyuk National University and majored in atmospheric science. He is also involved in the science team for GEMS, which is the Geostationary Environment Monitoring Spectrometer on board the GeoComSat, which is the Korean Geostationary Meteorological Satellite, as well as the science team for CHORUS AQ, the Korea-United States Air Quality Study. Since joining us at AOS in 2019, Jongjin has worked with our group here to improve thermodynamic retrievals from the ARIE instrument. And that will be the topic of his presentation today. So let's welcome Jongjin.
Okay, thank you, John, for nice introducing. So, can you see my screen and can you hear me?
Mm-hmm.
Okay, so thank you for attending to my master's seminars. My name is Jongjin and I'm working with John and Tim and Dave and Tristan. Today, I'm going to talk about using multiple scanning angles to improve ARIE thermodynamic retrieval. So it is very important to measure the temperature and humidity near the surface and in the planetary boundary layers. The planetary boundary layer is established by wind drag and buoyancy force, and it is the lowest part of the atmosphere where we live. So its behavior is directly influenced by its contact with the surface, and also it has very high variability on the days. So the thermodynamics of the PBR is the key component for a wide range of applications, such as severe weather nowcast and forecast, and initialization for numerical weather prediction models. And this is also connected with dispersion of pollutant and exchange of heat and waters. So 2017 decadal survey highlighted the importance of thermodynamic profiles in the PBR and also prioritized designing observations of the PBR as an area for future investment. So there are many thermodynamic observations we have. This figure shows the global observing systems, and it consists of many in situ measurement and the spaceborne and ground-based remote sensing. First, in situ, such as radio zonde and tower and airborne, has very high accuracy and vertical resolutions, but it has limitation to temporal and spatial resolutions with respect to globe. And spaceborne remote sensing or satellite has benefit of wide coverage on a global scales and also improvement of forecast skills in global numerical weather prediction models. However, it has relatively coarse vertical resolutions and a lower accuracy, especially in the PBR and near the surface. And last, ground-based remote sensing has very high sensitivity and vertical and temporal resolutions, especially near the surface. So it can be complemented with those two observations. So there are two operational and commercially available ground-based remote sensing measurements: microwave radiometers and atmospheric emitted radiance interferometers. And those two measurements also have global network. So microwave radiometers retrieve vertical structure of temperature and humidity using ozone absorptions and water vapor absorptions in microwave regions. And also we can get the liquid water pass and cloud informations from microwave radiometers. The MWR community has used multiple scanning angles to improve retrievals below 1 kilometer. And atmospheric emitted radiance interferometer ARIE also retrieved the vertical structure of temperature and humidity using CO2 absorption and water vapor absorption in infrared regions. However, ARIE has only used single zenith view because original ARIE is designed to view zenith. So our scientific question was coming from here. Using multiple scanning angles will also improve the ARIE retrievals, and we studied about that, and we will look at this. ARIE was developed for the ARM programs by SSEC at UW-Madison. The spectral range is from 500 to 3,000 wave numbers with very high spectral resolutions less than 1 wave numbers. And the temporal resolutions is 20 seconds, and the radiometric elevation is better than 1% of the ambient radiance. And ARIE also has many applications, not only retrieving temperature and humidity, but also retrieving cloud information and developing infrared radiative transfer models and characterization of dust properties. This figure is the marine ARIE, which is designed to view water, ice surface, and slant skies. So it is usually on board on a ship. And this slide shows what is the multiple scanning angles and why it is expected to useful to improve retrievals near the surface. So for original ARIE, it observed a single downwelling infrared radiance coming from zenith. However, for multiple scanning angles, we will use the several radiance coming from different scanning angles. And this figure shows the relationship between optical path and scanning angles. The optical path S depends on the scanning angle data and the thickness of layer G. And it is defined as these two equations. So for examples, optical path of zenith is same as the thickness of layers. And optical path at 10 degree is 6 times as large as the optical path of zenith. So we thought that these long optical paths at low angles make the radiance will become more sensitive and have more information near the surface. So we have two different angle tests. The first test is two scanning angle tests, such as 10 plus zenith and 40 plus zenith and 80 plus zenith. And from this test, we will look at the characteristics of scanning angles to retrievals. And second test is multiple scanning angle test. For example, 10 plus zenith and 4 more scanning angles plus zenith and 8 more scanning angles plus zenith. And from this test, we will look at the effect of numbers of scanning angles to retrievals. And this is the optimal estimation method we used in retrieval algorithms. So the state vector X can be calculated using these equations. And in these equations, the state vector X is the vertical structure of temperature and water vapor mixing ratio. And we only use single TQ profiles because we assume the horizontally homogeneous atmosphere. And also the air covariance metrics of measurement and prior are considered in these equations. So I'm going to show two results. The first result is about the particle structure of temperature and water vapor mixing ratio. And second result is about information content or degree of freedoms. The information content, which is the trace of matrix A, can be calculated using these equations. And the information content means the maximum number of logically independent values, which are values that have the freedom to vary. And also we have two data sets. So the first data set, we called it synthetic experiment. So we simulated the infrared radiance using line-by-line radiative transfer models and Zonde TQ soundings. And we have Zonde soundings at 3 different sites of ARM: Southern Great Plain, SCP, and Tropical Western Pacific, TWP, and North Slope of Alaska, NSA. And these fixed 3 sites of ARM provide continuous and long-term data to improve climate research. And the scanning angles we have are 9 different angles from 10 to zenith with 10-degree gaps. And also we assume the homogeneous thermodynamic profiles and clear sky conditions. So this figure shows the example of SCP Zonde soundings, temperature, and water vapor mixing ratio. And this infrared spectrum is calculated using IBRTM and these Zonde soundings at different scanning angles, zenith and 30 and 10-degree angles. And this shows the simple flow about forward and inverse. So for forward, we make the synthetic radiance using ABRTM and Zonde TQ profiles. And for inverse, we retrieve the TQ profiles using ARIE algorithms and the radiance we have or we make. And we made prior profiles using 10 years Zonde soundings at each site. So this figure shows the mean and standard deviation of temperature and water vapor mixing ratio on January and July. And the black lines are SCP, and blue lines are NSA, and red lines are TWP. So first of all, SCP, the black lines, we can see it depends on the month. So cold and dry on January, and hot and humid on July. And NSA site has very cold and dry conditions on both January and July. So the mean water vapor mixing ratio near the surface is less than 1 gram per kilogram in winter and less than 5 gram per kilogram in summers. And TWP site has very hot and humid conditions, so water vapor mixing ratio are larger than 15 gram per kilogram on both January and July. The second data set we have is real observations during the ARM Cloud Aerosol Precipitation experiment campaigns. And this campaign was aimed to improve understanding and modeling of large-scale dynamics and cloud and precipitation processes associated with atmospheric rivers and aerosol cloud interactions. And as we can see in these figures, the location is Pacific Ocean and west of California. And we use the TSI and ceilometer information to filter out the cloud scene. And the scanning angles we have are 35, 30, 25, 20, and zenith. And the time difference between first 35 and last zenith is approximately 4 minutes. And also we made prior profiles using 10-year sonde soundings at Oakland and San Diego. During these campaigns, the most days were cloudy. So we only have 3 days where are considered the most clear skies from TSI and ceilometers data. 28th January and 9th and 10th February. So the first result is about information content at synthetic experiment. So this figure shows the vertical structure of mean information content and information content ratio of 2 scanning angle test. So y is altitude and x is the information content and information content ratio from these equations. And the black lines are single zenith, and red is 10 plus zenith, and blue is 70 plus zenith. So first, for the information content of temperatures, adding 10-degree angles has more information content than adding 40 or 70 degrees. And when you look at the information content ratio, most of information exists below 1.3 kilometers for red and 1.7 kilometers for blue and black. And it is because of the strong absorption of CO2 near the surface. So it makes the low scanning angles have more information near the surface, and also the spectral resonance becomes opaque faster at low scanning angles than at high scanning angles. However, the information content of water vapor mixing ratio, adding low scanning angles have more information content only near the surface, the red line. And at high altitude, adding high scanning angles have more information content than adding low scanning angles. And also, the 90% of information exists below 2.7 kilometers. It is higher than the temperature, because the spectral resonance for water vapors is relatively transparent than the spectral resonance for temperatures. So these 3 figures shows the information content ratio of water vapor mixing ratio at different 3 sites, SCP and NSA and TWP site. And we can see that at TWP site, most of information exists below 1 kilometers, and this altitude is much lower than SCP and NSA site, because TWP site has very humid conditions. So information content of water vapor mixing ratio depends on the humidity. profiles. So this figure is a box plot of information content at 4 kilometers of 144 profiles at SCP site. So Y is the information content, and X is the different scanning angles, and red box is temperature, and blue box is water vapor mixing ratio. So information content of temperatures, adding low scanning angles, 10, 20, 30, has more information content than adding high scanning angles. And for the water vapor mixing ratio, adding high scanning angles has more information content than adding low scanning angles. Because the strong absorption of CO2 makes low scanning angles contribute to increase of temperature information, especially near the surface. And for water vapors, high scanning angles can have information at higher altitude than the low scanning angles. And this is for NSA site. This is from NSA site. And also we can see the same characteristics of scanning angles. Adding low scanning angles have more information content, and adding high scanning angles have more information content of water vapor mixing ratio. And the information content are higher than SGP. And this is from TWP site, and we can also there are also same results with NSA and SCP site. Adding low scanning angle have more information of temperature, and adding high scanning angle have more information on water vapor mixing ratio. But the information content are much lower than the other two sites because TWP site have very humid conditions. So next result is information content of multiple scanning angle test. So Y is the information content, and X is the numbers of scanning angles. For example, 1 is single zenith, and 2 is 10 plus zenith, and 9 means 8 more scanning angles plus zenith. And we can see that the multiple scanning angles has more information content of both temperature and water vapor mixing ratio. So also the same with NSA result and TWP site. So this is the summary of information content at synthetic experiment. So this two figures shows the mean information content at 4 kilometers from 2 scanning angle test and multiple scanning angle test. So the solid line is information content of temperature, and dashed line is information content of water vapor mixing ratio, and the blue is NSA, and black is SCP, and red is TWP site. So at the left figures, we can see that adding low scanning angles has more information content of temperatures, and adding high scanning angles has more information content of water vapor mixing ratio. And also, adding more scanning angles have more information content of both temperature and water vapor mixing ratio. And these tables these tables are the mean information content at the different numbers of scanning angles from single zenith to 8 more scanning angles plus zenith. So information content of temperatures, 9 scanning angles have approximately 40% more than at single scanning angles by an increase of 1.5, 1.6, and 1.3. And for water vapor mixing ratio, it depends on the humidity. So the 9 scanning angles have 60% to 140% more information than single zenith by an increase of 2 at NSA and 0.4 at TWP site. So these are the summary of information content at synthetic experiment. So next result is about vertical structure of temperature and humidity. So these are the RMSE for temperature between Jonde soundings and the retrieved ARIE retrievals. So RMSE is calculated using these equations, and so y is the height and x is the RMSE for temperature, and the black is single zenith, and red is 10 plus zenith, and blue is 70 plus zenith at different site, SCP, NSA, and TWP site. So we can see that adding low scanning angles have better RMSE near the surface at both 3 sites. And also the result of 70 plus zenith blue lines and single zenith black lines look similar. And last, at TWP site, there is only small difference between single zenith and 2 scanning angles, except for near the surface. And these are the RMSE for water vapor mixing ratio. And also we can see the adding low scanning angles has benefit near the surface from single zenith. And also result of 70 plus zenith and zenith look similar. And also there is small difference at TWP site. And next result is RMSE for temperature at multiple scanning angle test. So at these times, red is 1 more scanning angles plus zenith, and blue is 7 more scanning angles plus zenith. And we can see that multiple scanning angles, it is clear that multiple scanning angles has benefit near the surface and in the below 1.5 kilometers and 2 kilometers. And also there is improvement at TWP site when we use the multiple scanning angles. And last, result of 4 more scanning angles plus zenith and 7 more scanning angles plus zenith look similar, the red and the green and blue. And the last result is RMSE for water vapor mixing ratio at multiple scanning angle test. So also we can see the multiple scanning angles has benefit below 1 kilometers for SCP and 2 kilometers for NSA case. And also there are improvement in TWP site. But different from those 2 sites, TWP site, the 7 plus zenith has shows better performance than because at humid conditions, adding high scanning angles has better benefits than adding low scanning angles. So these are the results about particle structure of temperature and water vapor mixing ratio. And next result is about real observations. So the first result is box plot of information content at 2 scanning angle test and multiple scanning angle test. So first, at 2 scanning angle test, there are same result from the synthetic experiment. Adding low scanning angles has more information content of temperature, and adding high scanning angles has more information content of water vapor mixing ratio. And also at the multiple scanning angle test, we can see that adding more scanning angles has more information content of both temperature and water vapor mixing ratio. So the 5 scanning angles have more 13% more than single zenith by an increase of 0.9. And for water vapor mixing ratio, 5 scanning angles have 19% more than single zenith by an increase of 0.5. And these are the RMSE for temperature. So the left figure is from 2 scanning angle test, and right figure is from multiple scanning angle test. So the black is a single zenith, and the different color means the different scanning angle combinations. So at the 2 scanning angle test, at the 2 scanning angle test, 2 scanning angle shows better performance near the surface, and these tables are the mean RMSE below 500 meters and 2 kilometers. And also we can see that 2 scanning angles have lower RMSE than single zenith. However, at multiple scanning angle test, we can see that the multiple scanning angles haven't necessarily good RMSE. And also you can see the same things in mean RMSE tables. And next result is RMSE for water vapor mixing ratio. And also at 2 scanning angle tests, we can see that adding low scanning angle has benefit below 500 meters, but above that altitude, there is no huge improvement with additional scanning angles. And also at the multiple scanning angles, these haven't necessarily good RMSE. So we can see that multiple scanning angles have worse RMSE than single zenith. So these are conclusions. So for information content, adding low scanning angle has more information content of temperature, and adding high scanning angles has more information content of water vapor mixing ratio. And also the information content of water vapor mixing ratio depends on humidity. So the dry condition is likely to have more information content. So NSA have more information than TWP sucked. And also using more scanning angles have more information content both of temperature and water vapor mixing ratio. So results about information content are same at both synthetic experiment and the real observation data set. But for RMSE, they are a little bit difference. So first, at synthetic experiment, adding low scanning angle has benefit at temperature and water mixing ratio near the surface. But when we compare between single genus and 70 plus genus, there is no huge difference. So adding one more high scanning angles shows similar result with single genus. And multiple scanning angles has benefit at both temperature and water vapor emission ratio below 1 kilometers. And we can see the same result with MWR research. And at humid conditions, the multiple scanning angle has less benefit than the other two sites, because there are only small difference at TWP site. And next conclusion is about RMSE at clear observations. So we can so the two scanning angles has benefit at both temperature and water vapor emission ratio. However, the multiple scanning angles haven't necessarily a good result, and we believe that the reasons are the ARIE is on board on a ship, and ship keeps moving during the observations, and also we use only small samples, 3 days and 62 retrievals compared to 14 jaundice soundings. For future work, we are going to use the real observations at mosaic campaigns during October 2019 to September 2020. And also, we found that the multiple scanning angle has no benefit above 1.5 kilometer from ground, because the spectral channels used in algorithm is opaque at that altitude. So we are going to try to find the new spectral channels for multiple scanning angle retrievals. And last, we are going to apply these multiple scanning angles to retrieve cloud informations, because the horizontally homogeneous atmosphere is likely to happen under the cloud conditions, and also cloud is very opaque in infrared regions, so that our low scanning angles might have benefit under the cloud conditions. So these are the references in presentation. Have any question about this? Thank you.
Yeah, thank you very much, Jongjin. We have a good amount of time for questions from the group, so please go ahead.
There was a comment in the chat from Grant. I don't know, Grant, you want to just unmute and mention that yourself?
Sure, I'll go ahead. It sounds like there's not many people clamoring to ask questions. So I had a comment, and it's just that it makes sense, as you demonstrated, that when you add measurements via additional scan angles, and assuming you're working with a perfect forward model, which is essentially what the case is when you're doing simulated retrievals, you should get improved retrievals. Unfortunately, adding those additional measurements can also add unwanted sensitivity to unmodeled radiance variances, which would be the case if you have an imperfect forward model, or there's other contaminating variables that aren't really included in the simulations, like maybe undetected thin cloud or thick haze or something. And the results could be made worse rather than better with those additional measurements. But I'm wondering whether, if you were to anticipate those unmodeled noise sources, if you want to call it that, whether it's imperfections in the forward model or it's unmodeled variations in the environment that's being simulated, whether just building larger assumed errors into the measurement error covariance matrix could help mitigate that sensitivity, and then you might start to see more improvement with the addition of the measurements rather than, in some cases, sort of a reduction in performance.
Okay, thank you. Yeah, I'm agree to that. Yeah.
And I guess that's really more of a comment or a suggestion for future consideration. It doesn't necessarily need a response right now.
Yeah, Grant, thanks very much. That's definitely very appropriate comment for explaining why we're actually seeing we're not seeing an improvement in certain cases, but that's what's tricky about these additional observations. So thanks.
Tristan, go ahead.
Yeah, thank you for the presentation. I think I like your, I think it was one of your future work elements here was to, number 2, I think, was to look at whether or not you might need different channels. I was thinking that as you were going along, that maybe doing some sort of a study of what additional channels you might be able to use to kind of maximize the information that you get from multiple scanning angles. I had, I guess, 2 questions related. The first is just because you applied the algorithm in multiple different locations with different humidity, I was wondering, right now, does the algorithm always use the same combination of channels at all of the different locations?
Yeah, same spectral channels.
Okay, same channels. Okay, and then so my question really was, what do you expect? What different channels, I guess, what do you expect to change if you were to do an analysis of, you know, what different channels you might want to use with the different scanning angles? I mean, do you have some idea right now of what might happen if you studied that?
Okay, so when I look at the information ratio for temperatures, the most of information exists below approximately 1 kilometer because the spectral legends become opaque at that altitude. So if we add the spectral legends where are the less opaque, so either useful to get the information above that altitude. So I expect that. So also there are mentions about this in MWR multi-scanning angle papers. So they also mentions that need to find more transparent channels to improve the retrievals at high altitude to get more data, to get more information. It makes sense to you?
Yes, perfect sense. Thanks.
Yeah.
So Tristan's question actually prompted another one of mine, and this may be information that I missed at the beginning. Are you using the entire ARIE spectrum, or are you using subset of channels that have been selected based on information content? You already said that you're using the same channels in retrievals for all environments, but it wasn't, I don't remember seeing specifically which channels are being included.
Oh, here. Oh, here. So we use the CO2 absorption band between 611 to 722, and we use the spectral legend for water vapors between 538 to 588.
Okay, so you're using ranges of channels that are associated with these absorption features as opposed to just a discrete selection of individual channels. Is that right?
Yes.
Okay, thank you.
Then one thing I just wanted to add quickly, one thing we did look at that Jongjin didn't have time to present is we did look at alternative spectral bands to use and how the information content varies for that. In addition, we also looked at adjusting the spectral region based on the angle, in that for low scanning angles, we want to look at more opaque channels so that we don't see too far where the atmosphere might become homogeneous. Whereas for higher angles closer to zenith, we use more transparent channels. So that's another future work where we can adaptively select channels based on the site and based on the scan angle to optimize for the specific measurement.
So I'm also noticing when I look at that list of, or the two ranges of channels that are being used, I don't usually think in per centimeter. I have to kind of convert in my head to micrometers, but am I correctly understanding the water vapor absorption that's being looked at there is actually on the far side of the CO2 band in the more kind of long wave beyond the CO2 15 micron band as opposed to the 6.3 micron band?
Yeah, 1.5. Yeah, the water vapor absorption band is longer. No. Wait.
I guess I just have to divide those numbers by into 20,000 or something like, or 10,000.
That's 18 microns. Those are around 18 microns. Yeah, it's on the far side of the CO2. And it's a nice region because there's nothing else that interferes there.
Okay, interesting. So I had previously assumed that whole region is very messy out there and not as well modeled compared with the 6.3 micron band, but apparently that's not the case.
Well, the ARIE does have good sensitivity there. So that's been very often used in this retrieval.
Okay, thanks.
And have you any other comment and question? Yeah. So, yeah. That's no. Okay. Thank you for attending today. Yeah, I very appreciated with you.
Yeah, thanks for a great talk.
Thank you, Pete.
Yeah, thanks, Jongjin, and thank you for all the comments.
I think we're off next week, so there'll be no department seminar next Wednesday, if I'm right, Gerald, and we'll be back on the 14th of April. All right, have a good long weekend, everybody. No classes on Friday, so no weather watch on Friday either. So, all right, take care, everybody.